I'm Norman Wildberger. In today's video we're going to look at circles, and in the next video we're going to look at spheres. But we want to introduce these objects using linear algebra and using especially this framework of the dot product or symmetric bilinear form that we've been talking about in the last few videos. This gives us a very flexible and general way of thinking about circles, which will be a little bit novel to many of us. And we get to think about these very fundamental things in a somewhat new way. So the linear algebra provides us with a framework for thinking and a language in which we can see things in a new way. So this is going to be a little bit challenging, especially for those of you who have been studying mathematics for many years. We want to open ourselves up to wider possibilities. In particular, this approach has very significant applications to modern algebraic geometry. Even though what I'm going to be saying is very elementary, still the implications are profound. All right, so the main issue is, what are circles? Okay, we're going to be talking about circles centered around 0 in today's lecture. They're the simplest ones, and they're perhaps the most accessible ones from the linear algebra point of view. Other circles are obtained by translation, and once we understand the circles around the origin, it's not too hard to simply translate that knowledge around. So the standard answer to what a circle is involving this equation here, x squared plus y squared equals k. And so one possible answer to the question, what is a circle, is that it's an equation of the form x squared plus y squared equals k. There's what we usually draw for a circle. But what we're really drawing here then is those points, or vectors in our case, that actually lie on the circle. And by that we mean that a vector x0, y0 lies on the circle precisely when it satisfies the equation of the circle, namely x0 squared plus y0 squared equals k. So here, for example, is a vector v, and all of our vectors for now will have their tails at the origin. So we're thinking about vectors and points pretty well interchangeably. This vector lies on this particular circle. We could say that it has quadrants k because this equation is really telling us that v dot v, or the quadrants of v, is k. Now, an important remark. Note that C is not defined in terms of a set of points. In the 20th century, it was very common to try to define or specify mathematical objects in terms of sets. Somewhat unfortunate development in my point of view, because, for example, here it requires us to have some prior understanding of infinite sets of points. And it also doesn't correspond to anything that our computers can really do, because our computers cannot hold the infinite set of points which ostensibly lies on this circle. It's much more efficient, much more natural to think of the circle as being the equation itself. Now there's an interesting other aspect to this story. That besides thinking about points lying on circles, it's also possible to think in terms of the relationship of lines with this circle. Now if you take this circle here and you take this vector x0, y0 which lies on the circle, then this tangent line here will have equation x0 times x plus y0 times y equals k. Let's see why that's plausible. So this is certainly a line if we think of x and y as being the variables and x0 and y0 as being fixed points. So this is certainly a line with normal vector x0, y0. We recognize those coefficients are giving us the normal vector. And furthermore, this line passes through the point v, because if we replace x and y with x0, y0, we get x0 squared plus y0 squared, and we are assuming that x0, y0 satisfies that equation. So yes, this point does lie on that line, and furthermore, this line is actually perpendicular to the vector. So that's a tangent line. And so another way of thinking about this circle is in terms of the lines that lie on it. Okay? This is a very familiar point of view to a classical geometer. Now you can think about this circle as being a whole bunch of points, but you can also think of the circle as being defined by this envelope of lines. And at some level, those two different ways of looking at things are sort of at the same par. Not intrinsically better to think about points or lines in the plane. They're kind of dual objects in a way. So this is pointing us, in fact, to an alternate definition of a circle. Okay, so what I'm going to ask you to do, I know this is a very familiar point of view, but I'm going to ask you to open your mind to a slightly different possibility of what the circle is. Okay, we're going to introduce a variant of this, or maybe a generalization, a bit of a wider picture that will allow us to see this circle in a new light. And this new way of thinking about things is definitely motivated by our prior study of the dot product. All right, so let me remind you that if you have a vector, xy, we've defined the quadrants of the vector xy, which is x squared plus y squared. So given a vector, we get a number. And this association is a kind of quadratic function in that the entries of the vector get represented quadratically. Mathematically, we call this a quadratic form. So a quadratic form is a function on a vector space, which is essentially a quadratic, like this one is. But we've also talked about the dot product, which is a variant to this quadrants. And the way we've set things up, it's actually prior to the quadrants. So remember that the dot product of two vectors, x1, y1 dot x2, y2, is this number x1, x2 plus y1, y2. And that's a symmetric bilinear form. It's something that inputs a pair of vectors and gives us a number. And it has the distinction that it's now linear in both of the inputs. It's not a quadratic function of one thing, it's a linear function of two things. Bilinear function. Okay, so I think a fundamental insight is that the symmetric bilinear form is generally more fundamental than the quadratic form. You should think about the quadratic form as coming from the bilinear form. Okay, this is a point of view, admittedly, to a certain extent, but I've thought about this issue for many decades, actually. And I'm firmly convinced that this is really the right way of thinking about things. It's the symmetric bilinear form which is the key object. In other words, the dot product. All right, so that gives us then an option of thinking about a circle in a slightly different way. So here's the way we had been thinking about it. As the equation x squared plus y squared equals k for some number k. That's definitely a quadratic form kind of definition because we're utilizing this quadratic form directly. There is now another way of thinking about it, which we might call the symmetric bilinear form definition of the circle with center 0. I didn't put 0 here, let's put it here. With center 0. And now this equation has the form, well, this dot product equals k. x1, x2 plus y1, y2 equals k. So this is a quadratic form kind of equation or object. This is a bilinear form kind of object. We're going to start thinking about a circle this way. Okay, this is unfamiliar, probably to many of you, unless you're a classical geometer. If you're a classical geometer, this is a very natural and reasonable thing to do and will be very familiar. But most people these days have not been exposed to a lot of classical geometry, unfortunately. So this will be a novel point of view, even to many algebraic geometers. Okay? So it's a new idea that a circle is really that equation right there. It's an equation involving two vectors and a particular number k. All right, so here's our alternate definition of a circle. that a circle is actually an equation of the form x1, x2 plus y1, y2 equals k for some fixed k. All right, now if we adopt this point of view, let's call this equation star, then we can say that a pair of vectors v1 equals x1, y1 and v2 equals x2, y2 are conjugate or dual with respect to c precisely when they satisfy the equation. So in other words, satisfying the equation is something that a pair of vectors do. And when a pair of vectors satisfy the equation, we say that they're in a certain relation. And the relation is conjugation, or more usually duality. In this case, we are going to introduce some notation. We're going to say that v1 and v2 are perpendicular with respect to c. All right? This is a new kind of notation, and this just means that with respect to this circle, that v1 and v2, that pair, satisfy the equation of the circle. And one more very special case, very important special case, to recover the earlier definition is this one. We'll say that a single vector v, x, y, lies on the circle precisely when v is perpendicular with respect to c to itself. In other words, precisely when the pair v, v satisfy the equation of the circle. Or when x squared plus y squared equals k. So we recover the earlier definition by setting the two vectors equal to each other and asking which vectors satisfy that property. But more generally, we have this more flexible notion now that allows us to talk about pairs of vectors satisfying the equation, even if they are not the same. Okay, so let's illustrate this with this particular circle here. Okay, here we have a vector v, which actually lies on the circle. It has quadrants k, x squared plus y squared equals k, and okay, we recover the usual picture of the circle by drawing those points v that will actually lie on the circle. But now we also have this other kind of relationship between pairs of vectors. And I'm going to express that geometrically by showing you a vector v1. And so I'm thinking in terms of fixing x1 and y1. And then I'm going to show you all the vectors v2 that are satisfying the equation together with v1. Right? So if we fix x1 and y1 and think of x2 and y2 as being variables, then that's an equation, a linear equation in x2 and y2, which defines a line. So every point on this line, say v2, has the property that v1 together with that v2 satisfy the equation of the circle. And I'm going to introduce this notation for that line. It's v1 perp with respect to circle. So these are the vectors, lying on this line are the vectors which have the property that v1 is perpendicular with respect to c to v2. And it turns out that if you move this point around, well, this line will move too. If the point moves closer in towards the center, the line moves out. If the point moves closer to the boundary, it moves closer to being a tangent line. And then when the point gets on the other side, well, then the perpendicular line looks something like this. So for example, here is another vector w1, and here's its perpendicular with respect to c. So here are all the points, say w2, so that these pairs of points satisfy the equation. So this point together with this point satisfy the equation. This point together with this point satisfy the equation, etc. True for all those points on the line. So what we get here is you can think of it as sort of a matching between points and lines. Now for every point, we have a line that's determined by that point and the choice of the circle that we're starting with. So we see that the circle is not just a set of points. For sure it's not. That's a very limiting way to think about a circle. Okay? So you have to let go of some thinking here. Don't think about a circle as a set of points anymore. I want you to think about a circle as being this duality between vector v1 and vector v2. It's a relation that's satisfied by pairs of vectors. Alright, so in this way, the theory of circles ends up sort of sitting inside linear algebra, because this is really a completely linear object. It's bilinear. It's linear in v1, it's linear in v2. So the quadratic aspect of the circle that we're familiar with somehow gets extended into a bilinear aspect. So a circle becomes a bilinear object as much as a quadratic one. This definitely does take some getting used to if you haven't seen it before. Okay, so let's have a look at 3 specific examples. And all of these circles are completely dependent on the k value that's on the right-hand side. But all the circles are the same, except for the right-hand side. So what I'm going to do is I'm going to choose 3 particular k values. And I'm going to choose the 3 most important k values. All right, there are 3 numbers which are more important than any other numbers, and I hope you all know what they are. Okay, so the first one is the number 1. Okay, so we're going to look at the circle whose quadrants k is equal to 1. Here is the traditional equation for that circle. X squared plus y squared equals 1. We call it the unit circle. We draw it like this in the familiar way, going through the points with coordinates 1 and minus 1, 1 and minus 1 along the x and y axis. Now we're sort of graduating to this bilinear point of view, where we replace this quadratic expression with this bilinear expression involving 2 vectors. So x1, x2 plus y1, y2 equals 1. Okay, so the bilinear definition of C1, this one here, yields an important duality between a vector, v, say x0, y0, and its dual line. Okay, this is our notation for the dual line, v perp c. This is what we get when we just substitute x0, y0 into the equation and let the other x and y be variable. So we get the equation x0x plus y0y equals 1. So for example, if we choose this particular vector v, which is 3/5, 4/5, which is a vector that lies on the line, then the corresponding dual line is the line 3/5 x plus 4/5 y equals 1. And as we've seen, that really is a tangent vector to the circle because it's a line whose normal vector is v, and that actually does pass through that point. So we call this line v perp with respect to c. But we can do this kind of thing not just for a point on the circle. We can do this for pretty well any point. For example, if we choose the point w equals -2, -1, there it is there, then that also has a dual line, given by the equation -2x minus y equals 1. That line is right there. So this is the line consisting of vectors, or points, which are perpendicular to this one in this sense, in the sense of satisfying this equation. So for example, this is a vector here that's on this line, this point 0, -1. Okay? So if you plug 0, -1 in here, you see that it is satisfied. So that this vector and 0, -1 are perpendicular with respect to c. So we get this association between points in the plane and lines, which remarkably is not at all new. It's in fact thousands of years old. It's a duality called polarity in geometry. And it goes back right to the Greek genius who was the master of conics. to Apollonius of Perga. So this is a very classical notion that's just coming here into the picture because of our insistence on using the dot product to frame things. So you look at the dot product, you try to see a circle in terms of the dot product, you automatically get this polarity of Apollonius. This is a key indicator that we are on the right track, that this is a good way of thinking. And if you have watched any of my universal hyperbolic geometry series, which I hope you have, or at least I hope you are intending to, you will see that this polarity and what we're talking about here is absolutely central to hyperbolic geometry. It's impossible to understand hyperbolic geometry properly without really coming to grips with what I'm saying right here on this slide. Right? This is the start of hyperbolic geometry. Although we're not going to be talking about that in this course, but if you have an interest in this subject, Universal Hyperbolic Geometry, or my papers by essentially the same title, Universal Hyperbolic Geometry 1, 2, 3, 4, they're the places where you get a whole new world of hyperbolic geometry opening up from this point of view. All right, so that's the unit circle looked at now in a new way. All right, so the unit circle is now an association between pairs of points, or maybe a little bit more geometrically between a point and a line. You move the point around, the line moves around. Something like this. Okay, my finger is the point. Oh, down here. Of course, if the point actually gets to the origin, well, something a little bit strange happens. Then the line actually goes to infinity. And properly speaking, we really need some points at infinity to make this picture completely a good correspondence between points and lines. But we don't need to worry about that right now. We're just going to think about this in terms of the vector plane. So that's our first example, the unit circle. All right, so what's the second most important number after 1? The second most important number is 0. And so that's our second example. We're going to look at the circle, say C0, which is traditionally given by x squared plus y squared equals 0. And now, with our bilinear point of view, it actually corresponds to the equation x1, x2 plus y1, y2 equals 0. And now we start to see even more clearly the big difference in power from going from this kind of quadratic point of view to this bilinear point of view. From the quadratic point of view, the circle x squared plus y squared equals 0 is highly uninteresting because there's only one point on it. 0, 0 is the only vector that lies on that circle. So as a geometrical object, it might seem to be rather uninteresting. But that's actually far from the case. This is actually a very interesting circle, because the associated polarity is actually the original dot product itself. Okay, so there's only one vector that's actually lying on C0, namely 0, 0. But in this case, the perpendicularity with respect to the circle, in other words, V1 is perpendicular with respect to C0 to V2, precisely when V1 and V2 satisfy this equation. And that's exactly the condition of regular perpendicularity between two vectors. So perpendicularity with respect to this circle, in the sense of satisfying this equation, is the same as the regular perpendicularity of Euclidean geometry. So for example, here's a vector v, which maybe is 4/3, 1/2. Then the vectors which are perpendicular to that in the sense of satisfying this equation are all the vectors lying on this line here, which is the perpendicular line. And it has equation 4/3 x plus 1/2 y equals 0. So more generally, the dual of the vector x0, y0 is the line x0x plus y0, y equals 0. And, well, that's the perpendicular of v with respect to c0, but that's in fact the same as the standard perpendicular of the vector. So we're recovering the dot product here with respect to this circle. This bilinear form associated to the circle is recovering the usual dot product. And the association of vectors to lines is just a very simple one of associating to any vector the line through the origin which is perpendicular to that vector. Excellent. So what is the third most important number? It's -1. After 1 and 0, -1 is the next most important number because it's the inverse of 1 additively. So we're going to regard the circle C sub -1, which has quadratic equation x squared plus y squared equals -1. Well, that's a pretty uninteresting circle when you view it in a traditional way, because there aren't any vectors that lie on it. At least if we're working over the rational numbers. Of course, if we extend our field to, say, complex rational numbers or some such thing, then yes, maybe we could find points. But over the rational numbers, there are no points. So there's no real picture that we can draw. Nevertheless, you see that I'm still drawing a kind of picture. I'm drawing the unit circle kind of in a dotted or ghost-like fashion. And I hope you'll see why in a second. So here is our preferred bilinear definition of the same circle. C minus 1 is the equation x1, x2 plus y1, y2 equals -1. That is a very much alive equation. Okay, and in fact turns out to be very, very important for classical geometry. It basically connects very closely with spherical or elliptic geometry. All right, so if we have a vector, say 3/5, 4/5, which I've drawn there, that happens to be on this sort of ghost circle, then the dual line will be 3/5 x plus 4/5 y equals -1, or I could write +1 equals 0. And that turns out to be a line there, which curiously is also tangent to the this ghost circle. In fact, it's tangent to the negative of this vector here. If we flip that vector in the origin, there's its negative, then this line is exactly the tangent line to this ghost circle through that negated point. So this is the vector v. That's its perpendicular with respect to this circle C equals C minus 1. And for a general point x0, y0, here's the general equation of the dual line. Okay, so as I mentioned, this is very important for spherical geometry, or more precisely elliptic geometry. And maybe I will not be able to tell you about that, but in the universal hyperbolic geometry series I will explain that in greater detail, and you'll see exactly why that is. So in particular, as we vary this point, what happens to the dual line? Well, as the point, say, moves out like this, then the dual line moves in. Moves out, moves in. And on the other hand, if the point moves in like this, then the dual line moves out and goes off to infinity as we get closer to 0. Of course, the theory of circles is very rich geometrically. We are actually in a pretty good position now with this framework of the dot product and linear algebra and vectors to actually derive and develop a lot of this theory of circles. This is not really a course in geometry, so I'm not going to do that to any great extent. But I'd like to at least show you a few theorems that are interesting and sort of relevant for our discussion. Okay, so some fundamental facts about circles. Let's first of all fix a particular circle. Okay, so maybe the circle v1 dot v2 equals k. That's another way of writing our bilinear form for a circle. And here's the quadratic form. This is sort of the old version. This is the new improved version, if you like. And here's going to be our picture of the circle. So we're not really choosing any particular k. Okay, so the first theorem is that if v0 happens to lie on C, for example here, then the dual line v0 perp with respect to C is the tangent line to C at v0. So we've seen this in special cases, but this is a general fact that you have a v0 on the circle, and then you look at all those vectors that satisfy the equation v0 dot that vector is k. That's going to give you a line, and that line is actually a tangent line to the circle at v0. Now I have to tell you what is a tangent line. And if you've studied calculus, you probably think, oh, now he has to invoke derivatives and limits and such things. Okay. But no, we don't have to do that because we're working algebraically. We can define tangents of circles purely algebraically. No calculus in sight. Here's the definition. So a line L is a tangent to the circle C precisely when L meets C in exactly one vector. So this line meets the circle at exactly this one vector, which is to say that there's exactly one vector which lies on the circle and lies on the line. Some lines will have no vectors that they share with the circle, for example that one. And other lines, for example this one perhaps, may have 2 points that it shares with the circle. So as a tangent is the special case that's between those two general cases where there's exactly one point that lies on the circle and the line. That's the meaning of the theorem, and this is very important and perhaps you might think obvious theorem, and it is. It's not. We've basically indicated the proof already. But we'll see that as we get to a more general situation, this theorem becomes still interesting. All right, so our next theorem concerns still the same circle, and now 2 points or vectors which lie on the circle. So suppose that v1 and v2 lie on C, and the tangents at those 2 points, so v1 perp with respect to C, and v2 perp with respect to C. Suppose those two lines meet at the vector u. All right. Then the claim is that the perpendicular of u with respect to C is the line through v1 and v2. So that's in fact telling us a way of thinking about what the dual line is. If you have some vector outside the circle like this, then a way of visualizing what the dual line is that it's the line that joins the 2 points of tangency that you can make by drawing lines from u to the circle which are tangent. Okay, so you have the point u, you draw the tangents from u to the circle. There's 2 of those. See where they meet. That gives you the dual. And I remind you that means that if you take the dot product between u and any vector on here, you're going to get k. That's what the duality means. That u dot anything along here is always k. That's what we mean by the pair satisfying the equation of the circle. Okay, in the next theorem we're going to go up a little bit to 3 points on the circle. Now we have v1, v2, and v3 on C. And we have 3 tangents. Tangent at v1, tangent at v2, tangent at v3. And let's suppose that those tangents meet at the points u1, u2, u3. Labeled like that. So the u1 point is the meet of the tangent at v3 and at v2, etc. Then the theorem says that the triangle v1, v2, v3 is perspective to u1, u2, u3. So this triangle here, inscribed in the circle, is perspective to this triangle circumscribed to the circle. Now what does that mean? Well, it means that if you join up corresponding points with lines, so you join up v1 with u1, and v2 with u2, and v3 with u3, then those 3 lines are concurrent at a point. All right, now for our last and crowning result today. a theorem that actually goes back to Apollonius. Now we have our circle C, and we have 4 points lying on the circle. V1, V2, V3, and V4. Okay, so the meaning now is the following. So if you have 4 points, often called a quadrangle, then those 4 points determine 6 lines. Okay, so you can join V1 and V2, V1 and V3, V1 and V4. You can join V2 and V3, V2 and V4, and you can join V3 and V4. 6 lines. And those 6 lines, of course, they meet at the points V1, V2, V3, V4, but they also meet at 3 other points. So V1, V4, and V2, V3 will meet at some new point. Let's call it R. And V2, V1, and V3, V4 will meet at some new point. Let's call it T. And V2, V4, and V1, V3 meet at some new point. Let's call it S. So these points R, T, and S are usually called the diagonal points of the quadrangle that we started with. Okay. We don't have to have 4 points on a circle to do this. We can do this for any 4 points in the plane. We can always draw these 6 lines and get these 3 extra points, which are called the diagonal points of the original quadrangle. This is projective geometry, where we're just using a straight edge to connect points and drawing meets of lines. Those are really the only 2 operations. Okay, now what's the result? So the theorem says something spectacular happens with these 3 points R, S, and T that we construct this way. And here is the statement, that R is perpendicular with respect to C to S is perpendicular to T, and R is perpendicular to T. Should have an arrow here. So these 3 vectors are mutually perpendicular with respect to the circle C that we're starting with. And what does that actually mean? Well, it means that if you take the dot product between T and S, you're going to get K, the same K that you get when you dot V1 with itself, or V2 with itself. So the dot product between this vector and this vector is K, the dot product between this vector and this vector is K, and the dot product between this vector and this vector is K. Another way of saying what that means is that the dual of this vector T is this line here. This is then the line of vectors, so that when you take the equation of the circle T with one of these vectors, you're going to fulfill the equation of the circle. So the dual of T is this line, the dual of R is the line ST, and the dual of S is the line RT. It's a beautiful fact, and it's a fundamental fact about a circle. It's really a core fact of the universe, okay, discovered by Apollonius. And it's critical for projective geometry, it's critical for hyperbolic geometry, and it's just a lovely thing. Okay, so we're seeing it here that we can access this kind of theorem with our framework of dot products. We have all the language required in order to say what's going on here. In fact, we have also the tools to prove things. Although proving this result takes some significant amount of work. Not so easy. So we're going to postpone proofs currently, because ultimately we want to think about these things not just for the circles that we're looking at here, but other kinds of more general situations too. But a good exercise is to verify these theorems that I've shown you. So one way of doing that would be just to use a dynamic geometry package like GeoGebra or CAR or Geometer's Sketchpad or Cabri or Cinderella. And by the way, GeoGebra and CAR are free, so you can download them and start playing in 10 minutes. So you make some circles, draw some points, make some lines, check that this kind of thing is happening. All right, so this is a very good introduction to circles. I have asked you now to think about circles in a new way, perhaps for many of you. It'll require, mulling it over, starting to think in a bilinear way with two objects rather than just a quadratic way with one object. Okay. Very, very powerful point of view. As I said at the beginning of my lecture, once algebraic geometers fully appreciate the power of this point of view, I think it will change things for them considerably. All right, so in our next video in the series, we want to extend this thinking now to higher dimensions. We want to go to 3 dimensions. Okay? So we want to extend our understanding of circles to spheres. But of course, before we do that, we'll have to talk a little bit about the dot product in 3 dimensions, okay, which is not that much of a step, really. One of the beauties of this framework is that it generalizes to higher dimensions reasonably easily. There are often some new features, and we'll see some of them, but in essence, the direction is pretty easy to see. All right. So next time, we're going to talk about spheres and dot products in 3 dimensions, following on from this discussion. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.